Imagine Instagram or Twitter. A famous celebrity or influencer uploads a photo. It receives millions of likes and thousands of comments within minutes. Now scale it. Hundreds of thousands of influencers and celebrities with more than 100,000 followers. And even if each celebrity gets an average of 1,000 comments in a day, there will be a total of 100 million comments written every day. All of these comments will go in a database in a table somewhere. And assuming each row contains 1 kilobyte of data, 100 million comments would mean 100 gigabytes of data. And that's only per day. Transpose it for a year, this will be 36.5 terabytes of data, and that's only for comments. There is a lot more data that's stored in the database. Now, granted, modern managed databases can allow this kind of storage, but think about scaling. The influencers, their posts, and their comments are all going to increase with time, and so will the need for storage. At some point, we will hit a ceiling and will not be able to store the data in a single database forever. In addition to this, if one celebrity gets too viral than usual, the amount of writes may overwhelm the database, and it is possible that the database crashes, bringing down the entire application. So how do we handle this large amount of data and also reduce the probability of database crash? The answer lies in sharding. But before we jump onto that, we need to understand a concept called data partitioning. Now let's talk about the comments table where 100 million entries are written every day. Now, even though we may have that amount of storage and infrastructure, having such a huge table may lead to performance issues as the table grows. The lookups in the table may become slower and the indexes present in the table will also grow larger. So a better way to handle this is to split the data into different tables. So instead of a single table for comments, let's say that we have 10 tables with exactly the same schema. But the data is being split across these 10 tables. So naturally, the 100 million entries per day will be split across 10 tables, each of which will roughly have 10 million entries per day. It's not great, but it's certainly better. Similarly, if you have 100 tables, each table will then hold 1 million entries per day, which is significantly better for performance compared to 100 million entries in a single table. This way, we can tune the performance a little bit. But this comes with another problem. So imagine that a comment is written for a particular post and goes into the first table. And then another comment for the same post is written and goes to another table. Therefore, the comments for a single post can be distributed among different tables. Now, when someone tries to see the comment section of that post, the application has to query all the tables instead of just one table, join the results and order them by timestamp or popularity before returning it to the user. Now here, although we did have a uniform distribution of data, but we probably ended up with even worse performance. But what if we ensured that all the comments of a particular post are always written in the same table? For example, all the comments of post A go in one table, and all the comments of post B go in another, and so on. If we could somehow achieve this, we will only have to look up in that one table for all the comments of a particular post, and that would solve our problem to a huge extent. To achieve this, we have to introduce something called a partition key. A partition key is basically one of the columns of your table based on which you split the data. So in our case, we want to ensure that the comments of a particular post always go in the same table. Since posts are represented by post ID, we will define our partition key as the post ID. So whenever a comment comes in, we simply extract the post ID from the request and then we hash it in such a way that it gives us the table number. And once we have the table number, we can easily insert it. Similarly, for the next comment of the same post, the hash of the post ID will result in the same table number, thus ensuring that all the comments of a particular post always land up in the same table. If you want to know more about hashing, feel free to check out my other video on hashing where I explain this concept in much more detail. So, at this point, we have understood why we have to split the data and how to pick up a partition key. In a system design interview, if you are ever confused about which column you should pick as the partition key, don't think about how your data will be stored. Think about how it will be retrieved, and that will give you your answer. In our example as well, we thought about how the data will be retrieved. That is, we have a post and we will retrieve the comments of that post. So naturally, we should store our data in such a way that it is collected by the post ID. Now that we have understood data partitioning and partition key, the concept of sharding will seem like a cakewalk. Sharding is a concept in which you split a single write instance of a database into multiple instances along with its data. At first, you will still have to partition the data, but instead of keeping all these partition tables in a single database, you keep each partition in its own dedicated database. The logic of partitioning the data, partition key, hashing, and all those concepts will still apply, but now at an instance level instead of the table level. Each of these instances is called a shard, and our partition key will then be called a shard key. In addition to this, each of these shards will also have their own set of read replicas. In real life, it may also be possible that in a single shard, you may have even further data partitions. In that case, the shard key may be different from partition key. But for this video, we will assume that one shard is one partition. Here, it becomes even more important to select your partition or shard key carefully, because if the comments of the same post are spread across multiple instances, then you will have to do lookups across multiple shards, which will be much slower due to network overhead. And these kind of queries which span across multiple shards are called fan-out queries. Although in most circumstances you may want to avoid fan-out queries, but in some cases they may be unavoidable. For example, if you had a comments history feature like YouTube, where you see all the comments that you have written, the comments might be split across multiple shards because you wrote them on multiple posts or videos. In this case, your comments will be fetched using a fan-out query, which is quite acceptable because comments history is not something that users visit frequently, and nor is it latency sensitive. So your partition or shard key of post ID would still stand and will handle most latency sensitive use case, that is the view comments of a post, while making a trade-off for fan-out queries in case a user wants to see their own comments history. That's a perfectly acceptable trade-off. In a system design interview, make sure to highlight these things with your interviewer to show that you have a deep understanding of customer impact while choosing a shard key. At this point, sharding and data partitioning might seem like a perfect solution for scaling write-heavy databases while also mitigating a single point of failure. But it doesn't come without disadvantages. One of the most prominent caveats to sharding is hot shards. In an application like Instagram or X, the distribution of comments can get uneven. A regular user may post maybe once a month and may only get a couple of comments, but users who are celebrities or influencers post more frequently, with their posts getting hundreds or even thousands of comments. If we shard it by post ID, the database shards containing some of the popular posts will explode with comments, while others may not get impacted at all, and these kind of shards are called hot shards. The problem of hot shards can be mitigated in different ways, depending on the problem. For example, if the writes get too overwhelming for a single shard, you can shard it even further by using a secondary shard key. Whereas if the reads get too overwhelming, more read replicas can be added to that shard. Similarly, if a post gets too viral, it can be cached along with some of the top comments, and once you click view more to see all the comments, then the query gets redirected to actual database. And this can also shield your database from a lot of reads. Now, in our examples, we use post ID as the partition or shard key. But what happens when we need to add another database instance? We will have to update our hashing algorithm to incorporate the new instance. Let's say we do update it. Now, since the hash function is updated, it distributes the data in a different way. For example, if we previously had a post ID with a hash of 1234, all of its comments went to the first table according to the previous hash function. After updating the hash function, the comments of the post ID hash 1234 start going into another table. So all of this mumbo jumbo about keeping all of the comments of the same post in the same shard doesn't work when we need to add or remove databases. So how do we solve this problem? Thankfully, this problem can be easily solved by a very smart engineering technique called consistent hashing, which we will talk about in our next video. So stay tuned and don't miss it. Bis dann.